Hi class, we are on to chapter 3. So we are going to start discussing linear transformations and a lot more about matrices, right? So this is actually our introduction into matrices, but we're going to start with linear transformations, which is the equivalent of functions. Okay, a linear transformation is our function equivalent for linear algebra. Okay, so we're going to talk about linear transformations. There are such things as non-linear transformations as well, but we're going to stick to the easy ones, the linear transformations for today. Okay. So a linear transformation is a function which we label as t. We can give it any other name, but the general name is t for transform from Rm to Rn. What that means is I'm taking a vector that has m real entries and I'm sending it to a new vector that has n real entries. Now these values of m and n, they're arbitrary. They can be the same value, they can be different values. Really just depends on what we're talking about, okay? But we use m from the number of entries we're going from, and n is the number of entries that we're going to. Okay, now if I were to switch these around, then n would be the number of entries I'm going from, and m would be the number of entries I'm going to. Okay, so these things are interchangeable. They're not fixed values. Okay, they're just variables. I could have used a and b, r and, or I guess s and t, right? The general standard is m and n. Okay, so don't get caught up on the notation. So if you see m and n somewhere else, it does not have to be in this order. Okay, so a linear transformation is a transform from Rm to Rn such that for every vector u and v, so any two vectors that both have m entries each, okay, so they're in Rm, and a scalar, right, that's a real value, we have the following, okay? If I take u and v, those two vectors, and I add them together, and I plug them into my transformation, my function, then it's the same thing as if I were to transform one of those functions and transform the other function and add them together, okay? So the transformation gets to, it looks like a distribution, but it's not a distribution. It's actually the closure of addition principle, okay? So whether or not I'm adding inside the transform or I'm transforming the individual parts and then adding them together, I'll get the same thing, right? So that's closure under addition. The second property that we have for linear transformations, definition-wise, is that if I am taking the transform of a scalar multiple of one of these vectors, it's the same thing as if I multiply the output, right, the transform of that vector by the same scalar. So this is closed under scalar multiplication. Okay, so those are the two properties that we need to show. Closure under addition and closure under scalar multiplication, right? So these two things are our definition of a linear transformation. So for a transformation, we have a mapping from Rm, from where I'm at, into Rn, where I want to go to, right? So again, just think about these things as functions, and you should be used to what it is that we're going to be doing here, because we have a domain and we have a range. Our transformation takes something in the domain and it sends it to our range, right? So where we are to where we need to go, right? So if this is my vector space, Rm, right? So everything in here is a vector that has m components, and everything in here are things that have n components. My transformation takes the things from here and it sends them in the domain and it sends them to the range. So inside of the domain, it looks like a regular vector, and inside of the range, it looks like the transformed vector, the transformation of the vector, right? So what we like to say is that T maps a vector in Rm to a vector in Rn. It takes something from our domain and it sends it to our range. So let's do an example. So suppose we have a vector which we'll call x. So as x1, x2, x3 are the components. And a second vector y, which has components y1, y2, y3, right? So just to look, those are the things in my domain, right? So right now I'm in R3, right? These are in R3. That's my domain. Then what we call the cross product of x and y is given by the following. X cross product y has this sort of formula for it. Okay, now if you're in a Calculus 3 course, then you have or you will see cross product. If you've ever taken a different linear algebra course, you might have spent more time on cross product than we are. This is actually the only mention we're going to have of cross product. Again, in Calculus 3, you'll spend quite a bit of time on it. If you took in physics, you know all about the cross product already. So we're just going to kind of discuss it here in an example, and that's our definition of, or our exposure to, I should say, the cross product. So, x cross product y is given by x2 times y3, so x2 times y3 minus, and then the reverse of that, so y2 times x3. So the first entry in my cross product has nothing to do with the first entries of my two vectors. Okay, same thing here. The second entry in the cross product has nothing to do with the second entry of my vectors. It's all about x3 and y1 and x1 and y3. There's no x2, y2 in this second term. Same thing here. This is not going to have x3 or y3 in it at all. There's a nice way to set some things up to see how the cross product is supposed to work, but we're not really there yet in this course. So you don't have to worry about it because we're not doing a lot of cross product stuff in here anyways. Okay. So cross product has lots of good examples in physics. It helps to demonstrate the right hand rule. A lot to do with tensors and things like that. But again, it's not the focus of our example today. We're just going to be doing math on it. Okay. So what we want to do is we're going to let u be a fixed vector in R3. Okay. So real quick, just notice here, I'm taking vectors in R3 and I'm defining the cross product. And notice how many entries I have. I have 1 entry, 2 entries, 3 entries in my result, right? I'm going to say I have a fixed vector u, right? I don't know what this vector is. It's some vector, but it's not changing. And this vector is also in R3. And I'm going to define the transformation of t of some vector x as the cross product of u with that vector x. Okay, so just to reiterate, I have 2 vectors in R3. I'm defining a cross product. I'm taking a fixed vector. So these vectors, this vector will not change. These 2 vectors can be any vectors I want them to be. Okay. Now this vector is undefined, but is not a variable vector. It is a vector that does not move, right? U is also in R3. And I'm defining my transformation as the cross product of any vector that can change with my fixed vector. Okay, that's my transformation. So if I take the cross product of some vector x with this u in R3, I will get out another vector in R3 because the cross product gives me a 3-component vector. Okay, so what we want to do now is we want to show that t is a linear transformation. Very important here. Whenever they say the words show or verify, that means prove. Okay, this means we are doing a proof, right? So how do I show that something is a linear transformation? How do I prove that this is a linear transformation? Well, I have to go to my definition of linear transformation and show that this is true, that this holds true. Okay, so what I need to do is I need to take 2 elements from my domain and show that when I send them under my transformation to my range, okay, that this property holds. So if I take two vectors and I do this to them inside of the transformation, it'll be the exact same thing if I were to do a transformation of one and the transformation of the other and add them together. I should get out the exact same thing. I also need to show this closure under scalar multiplication. So I need to show closure under addition and closure under scalar multiplication. Now, the two vectors that I have in my case are not this u and x. Remember, u is fixed. I need it to work for any u and v in R, which is why I have these x and y defined here. Okay, so I'm going to take two vectors, x and y, and I'm going to add them together and then throw them inside of my transformation, which is the cross product with u, and show that it would be the same if I had did a cross product with u with just x or with just y and then added them together, right? So closure under addition. Now, it's been a while since I've actually made a video, so I don't remember how much proof stuff I've shown you already, so I'm going to go over this, assuming that I have shown you 0 proofs. I know I've shown you a little bit, maybe some really easy, basic ones. This one's a little bit more calculation based, which is actually good because it's more mathy, more stuff you're used to, rather than using a bunch of theorems to show that something is true or not. Okay, so again, I'm going to go over this just like if I have never shown you proof before. Okay, so remember, a proof starts out with a completely blank space. You have nothing. You have no vectors. You have nothing is defined. There's nothing for you to play with yet. So before you can start to prove stuff, you have to define what it is that you're doing. Okay, I can't just say, hey, look at this object and this object. When I add them together, I get this new object. Well, what are those objects? What do they look like, right? We have to define the things that we're using before we can start to use them, okay? So in this case, I need two vectors. So just from looking at the definition of linear transformation, I know I'm going to need two vectors and I'm going to need a scalar, okay? So in my case, I'm actually going to need three vectors because I have this fixed vector, right? So, so I have to say I have those four things, right? Those three vectors and the fixed scalar, and then I can start to do some math, right? So I'm going to say let u, x, and y be elements of R3. That means they are vectors that all have three real elements inside them. They could be square roots, they could be pi's, they could be -1/2, they could be 108.732 for the right. They just have entries that are real numbers. And I have a value that is a real value as well. So this is a single value, so it's a scalar. Okay. So now I have the things I'm going to start with defined, although I would like to say, what does it mean to have things in R3, right? So what I'm going to do is I'm going to talk about what happens when I have t of x plus y. Okay, so when I have my two vectors in R3 and I add them together and I plug that addition, that sum, into my transformation, what does that look like for me? So what does that look like? I'm going to have u plus y, I'm going to have x plus y as my variable, right? Because I'm plugging that in. So anything I plug in gets plugged into my function. So remember, u is fixed, but when I plug something in, it gets cross product with u. So if I'm plugging in x plus y, that is getting cross product with u, right? So then what is this going to look like? Well, I'm going to take the second component of u, right, u2, and I'm going to multiply that times the third component of what would be x plus y, which will be x3 plus y3. Okay, I'm going to subtract from that, right? So if x is the first vector, u is the first vector, I have to use u3, right? So that's going to be not x3 but u3, right? Because I'm using u plus u cross product something. So u cross product this is going to be u3, and then it's the second component of that second vector. So this is my second vector here. So x2 plus y2, right? Because remember, what's x1 plus y1? You're just adding the components together. And so I'm going to do that all the way down, just following this formula. Okay, following this formula. So if you look, it goes x2, x3, x1 for the first elements. So for u, it's the same thing, u2, u3, u1, right? On the second half, it's x3, x1, x2, u3, u1, u2. These, the order of the u terms match up with the x terms because those are the first terms in this whole cross product. Okay, so if you just pause this for a second, then you can see that this does follow this format. Right? Now, lots of times when I give this out for students to do themselves, they have lots and lots of problems trying to figure out exactly what they're plugging in and what they're doing. So I chose one that was a little bit more complicated to show you that it's just like plugging something into a function. Even if you're plugging in something weird to a function, that's what you're plugging in to your transformation, right? So your x plus y here should not be just you plugging in the formula for x cross product y. Okay, whatever you're plugging in for our example here, right, for this transformation is defined as whatever goes in gets cross product with this fixed vector. So if I'm plugging this in, it's going to get cross product with this fixed vector. So what we're going to do now is we're going to start to simplify this. Okay, now even though we're simplifying and you guys are all wonderful at math, we're not just doing this all willy-nilly. Okay, we are doing it one step at a time. Okay, so remember what I said, a proof should read forwards and backwards clearly. Okay, if I start to skip steps as I simplify, if I were to read this backwards and it did not make any sense, then that's not okay. I'm going to start to mark points off for those kinds of things. Okay, so my goal here, as I simplify, I want to go from this thing, which I just plugged in, that's all I did, I haven't done anything else to it, and I want to simplify to the point where I can start to separate everything into two different sums that mean the same thing as plugging in one of those vectors and cross producting with u, and plugging in that second vector y and cross producting with u. Right? So that's my goal. My goal is to take what I have and try to separate it so that it's equivalent to if I had started maybe here and worked backwards. Okay, so that's my goal right now. Okay, so we're going to do this in a smart way. A lot of times you should never get a proof on the first try. Okay, you should definitely be doing a proof with an eraser and a pencil, and you should definitely work in one direction. Maybe start at the go to the end of where you want to go and work backwards and try to meet yourself in the middle, right? So if I was having problems with this, I might do this math as far as I can, and then I might go, on the side of what I did here and do this, plug these things in and work out the math, and then see where they kind of overlap and where they connect, and then that would be my structure, right? I would put them all together, right? I would then take those two halves and put them together so it flowed cohesively to go from here into this representation, right? So that's a little trick that we like to do in the proof world. Proofs generally need side work. Okay, you're like me personally, a lot of times I can just blow through a proof, but that's because I've done years of proof writing. But even still in this class, when I write these lectures out, I have to kind of go on the side and do some rough drafts before, I make these fancy videos and things for you guys, right? So, so just a word of advice. You're trying to simplify this and you have an end goal in mind. If you can't get there, that's fine. Kind of reset yourself and start from your end goal and try to work yourself backwards. Okay, and then hopefully you can meet yourself in the middle somewhere, right? And then you can rewrite the whole thing so that it flows well. So I'm going to start to work my way down. So obviously, it doesn't make sense to do anything else except for to start to distribute these outer terms, right? So distribute this u2, this u3, etc., etc. And that's exactly what I'll do, right? So I got u2x3, u2y3 minus u3x2. This is a negative here. Do not forget to distribute your negative signs. I see this in calculus 3, differential equations, everything. People still make the little mistakes. You are not above that, right? So slow it down and make sure you're keeping check of your signs. And then I'll just do that with the rest of these, right? So this is what this will look like as you distribute all of these terms, right? So maybe take a second, use the pause button so that you can copy this down. Because I know I talk a lot, but I'm not going to waste a lot of time to let you copy this stuff, right? So from there, what we're going to do is we're going to start to rearrange things, okay? So remember, my end goal is to have t of x plus t of y. So what would t of x plus t of y be? Well, what would t of x be? T of x would be very much like this, but instead of the x and y, it would look like u and x, right? It should look like this. And t of y should look like u cross product y. So I want to rewrite these things so that it will start to look that way, right? So what I'm going to basically start doing is I'm going to group the x terms together, and I'm going to start to group the y terms together, right? So that's the next step. I'm separating my x's. I'm just moving things over, right? I'm not actually distributing or factoring anything. I'm just pulling out the x's on one side and the y's on the other side, right? Because again, what am I trying to get to? I want to get to from plugging in one thing to looking like plugging in two things. So I want to separate the x terms and the y terms from the left to the right side, especially since the way that I plugged it in was x first and y second. Okay. Oops. So I'm gonna just start to separate things. All right. So now, even though they are separated, I'm gonna start to put parentheses around things to show that I'm actually grouping them together. So these are actually my x stuff and actually my y stuff, right? And so if you look at the terms here with the u2x3, u3x2, that very much looks like the very first term here, right? So just a quick check for what the cross product looks like. Okay, so it looks like I have things in the right form, but the problem is, well, there is no problem, right? So I'm just grouping them together so that now I can say that I have u cross product x plus u cross product y, right? Because this is u cross product x plus, and then this is the u cross product y terms, okay? And what is u cross product x plus u cross product y? That is just the transformation of x plus the transformation of y. So that's that first portion, that closure under addition, right? So I started with this and I worked my way down to this. Okay, so remember, we are not done now. We just showed one of the two properties that we need, right? So just because we got somewhere and we got to some sort of a conclusion, that does not mean that we're finished, right? So the next thing that we need to do is we need to show the closure under scalar multiplication. So what does it look like if I plug in r times x? So what I want you to do right now is I want you to pause this video and I want you to work through this last half, okay? Try to do it without cheating, without looking through the video or the write-up. Just plug it in for yourself, work it to the end, and see how you did, okay? So I'll give you a couple seconds to pause it. And now that you are back, hopefully you did as I asked. We can go through this a little bit faster and I don't have to talk as much. And you can see how well you did, or at least what your thought process was versus the correct steps, right? So to plug in r of x into our transformation, we have our fixed vector u with the cross product of what it is that we're plugging in to our transformation, r times x, okay? So this scalar times x. So remember, we defined our scalar up here. So I can use it because it's been defined. I've already said, hey, this little thing, that's my scalar value. So what does that look like? is going to look very similar to our formula. Instead of y stuff everywhere, it'll be r times each of my x stuff everywhere with my u's, right? So we're just following the formula. So u2, rx3, u3, rx2, u3, rx1, u1, rx3, etc., etc., right? So now on the next step, again, let's think about where we're trying to go. We want to show that this will be the same thing as r on the outside times the transformation of x, okay? So the second closure under scalar multiplication, I have this. I've already showed what it looks like. This is what I'm trying to get to. It's actually pretty straightforward. I'm just trying to pull out this scalar multiple, okay? All the way outside of the transformation. So, okay, I have here, as you can see, I have an r on each term. So I'm not just going to pull it all the way out. I'm going one step at a time. Proofs go slowly. You're explaining to the reader exactly what you're doing. So if you start skipping a bunch of stuff, it's not going to be clear. I will take points off of proofs that skip through a lot of the algebra. Okay, I want to see everything. Okay, so to a certain extent. Okay, so here I'm going to pull out the r's, right? And then from here, the definition of a scalar multiple of a vector is you have r times every term. That's why I have to pull out the r, because if you skip a step, you're skipping the definition of a scalar multiple of a vector, right? The definition of a scalar multiple of a vector is that scalar times each element in the vector, okay? So the next thing I want to do is I'm going to pull that r out, and now that r is r times the transformation of u cross product x. That's what is going on right here, is u cross product x. So I need to make sure I stay that. That is r times the transformation of x. Therefore, the transformation of a scalar times u is the same thing as r times the transformation of u. So apologies, this should not be u. This should be x. Okay. I don't know why I put same thing here. This should not be u and v. Oh, okay, I see what I got. So what I'm doing is I'm writing the exact definition here, which is fine. But for me, I would give myself points off for what I did there. I should have wrote just not x and y. I should have wrote here x plus y is t of x plus t of y. Okay, because I haven't talked to my u in this case, and this proof is something different. So don't follow my example. Same thing here. It should be t of r times x is r times t of x. Don't go all the way to the definition, so that's my fault here. I'll fix that in the write-up, so apologies on that. But at the very end, we can say, therefore, t is a transformation from R3 to R3, given by t of x is u cross product x for a fixed u is a linear transformation. Okay, so we have to say that it's a linear transformation because this notation is for transformations, right? So we're showing that something's a linear transformation, not a non-linear transformation or you know, any other kind of thing like that. So this is kind of what you want your last line to be. Say what your domain and your range is with your transformation name, the formula that gives your transformation. Right here I was lazy and I just said u cross product x. I could have put the actual formula for it. I had to note that u is fixed, right? And that the end result is that this is indeed a linear transformation. Little black box means QED, or therefore it has been proven, or it has been shown. QED is the Latin term for it. I don't remember exactly what the terms for it are, the Latin words for it, but there you go. So right, so that's your first, or not your first, but that's, you know, a very involved proof. It's a very algebraic proof. It's not hard per se, but there is a lot going on. But that is a very, very standard level type of proof for this course. Right, so there is another method of showing something as a linear transformation. It's actually much, much, much easier. So obviously I need to show you the the correct way first before I show you a shortcut, because you're not going to understand the shortcut if you don't understand what it is that you're doing in general. So an alternative equivalency to this proof is to show both of these closures at the same time. Okay, so what I have down here is how you show closure of addition and closure of a scalar multiple at the exact same time. So that way you are combining the two together. Okay, so what I'm going to do right now, because I'm a nice guy, is I am going to, for extra credit for whoever is watching this right now, so this is for my spring term, okay, or I'm sorry, my fall term. If you redo the proof that I just showed you, but do it with showing closure of scalar multiplication and closure of addition and closure of scalar multiplication at the same time by showing this equivalency instead of showing the other two at the same time, I will give you some extra credit on your next towards your classwork assignments. If you are watching this for my class for a different semester, a future semester, let's say, just write a little note to me or send me an email, and then I will give you extra credit as well. Okay, so that's your first extra credit. It's not written anywhere, but it is on video, so you can hold me to that. Just remind me. Okay, so again, this shows both closure properties simultaneously instead of individually, as I did in the previous example. Okay, so I'm not going to show you how to do that now, but for this 3.1 classwork assignment, you can put at the very bottom extra credit. Show this proof. If it is correct, I will give you extra credit. I'll probably give you some partial credit for it too, but that is your extra credit opportunity. Okay. So now on to something a little bit different. We did talk about this a little bit, so we're going to talk about it a lot now. So the dimensions of a matrix are given as row first and then column. Okay. Or we'll say m by n. So again, remember, m and n varies. Okay, I can call this an n by m matrix. I can call this an a by b matrix. Don't get stuck on m goes first, n goes second. It does not have to. It's just however you want to write it. Okay, so this is my rows. This is my number of columns. Okay, I have m rows, n column. An easy way to remember this, okay, is rows first, columns second. Right? Well, how is that easy? RC. Okay. So when I was learning linear algebra, we said RC Cola because it was a very cheap Coca-Cola that you could buy. I think it was made by Shasta, which is based out of Hayward. But you had RC Cola, or you can just think about it as remote control, right? RC, like RC car, remote control. So RC for remote control, rows first, then columns. Number of rows, number of columns. So just a couple of brief examples. This would be a 2 by 3 matrix because I have 2 rows, 3 columns, right? 2 by 3. Oops. This is 4 by 2 because I have 4 rows, 2 columns. Okay. So just to mix it up a little bit, from what we've learned, this would be 4 equations, each of them having only 2 variables, x1 and x2, right? So 4, so number of equations, number of variables, right? But we never talk about it like that, only as rows and columns, okay? This is a 3 by 3, 3 rows, 3 columns, right? We call this an n by n matrix or a square matrix, right? A square matrix has the same number of rows as it does columns. Quick proof. An n by m, so again, if you notice, I reverse the order here because it does not matter. What really matters is that rows are first, columns are second, right? So if I have a matrix that has n rows and m columns, and I call it A, this is going to define a linear transformation from Rm to Rn, okay? From Rm to Rn by T of x equals A of x. So for your linear transformation, the order is reversed from your matrix, okay? So the number of equations you're going to see represents the space you're going into. The number of variables you have represents the space that you're in. Okay, so your rows and columns versus the order of your transformation is reversed. So think about it first. If this is your number of rows, that's the number of elements in your end result. Okay, so the first one for the dimensions is the last thing, or the size of your range. Okay, so just remember that they're reversed. So here the order does matter because we're talking about one specific example, one specific case. Right? Very, very important theorem right here. We're going to use this a lot, especially for linear transformations. So let's do another theorem. So let's say we have our matrix A that is composed of m vectors, and if it's an n by m matrix, then that means that each of these column vectors have n entries, right? Because that will give us an n by m matrix. And let's say we have our transformation from Rm to Rn. So remember, the number of rows is where we end up, and the number of columns, right, or the number of variables we have is where we start, right? So my domain to my range matches up with this matrix made out of column vectors. So this transformation is given by t of x equals a times whatever vector I multiply in there, right? So that's my transformation. Then a, right, w in Rn, so a vector in my range is in the range of the transformation, right? Because it has n elements, so it's in the range. So Rn is in the range of t if and only if the system a times x equaling this vector is consistent. All right, so what does that mean? That means that this is an output only if this equation makes sense. Okay, so if I were to put this, if I were to solve for this matrix equation, I should get coefficients that work for it, and those coefficients should be the elements of W. All right, so I have a unique solution for this if and only if this vector is inside of my range. Okay. The range of t is the same as the span of these column vectors. Now this should make sense as well. Okay, whatever vectors I can make by combining these vectors together in some way, right? All those combinations, those are all the possibilities of things that can end up in my range, right? So my range is the same thing as all of the things that get plugged into my transformation and, you know, get sent out. So the span of these is the same exact thing as the range of my linear transformation, right? So we've been talking a lot about domain, range, inputs, and outputs, right? So plugging in a vector and then getting a vector out, which is the same thing as multiplying my matrix times whatever I'm plugging in, right? So we need to start talking about one-to-oneness, one-to-one, and onto. Apologies for this, for it being offset. I couldn't get it to be all one single underline. This is weird. But anyways, one-to-one and onto. Okay, so these are terms that you hear when you talk about functions in algebra, and pre-calculus and things like that. Same thing here. Remember, all a transformation is basically a function. It is a function actually, right? So functions and transformations we'll see are exactly the same thing. So what happens when I'm one-to-one and onto? So what does that look like, and how do we determine that? So one-to-one and onto, right? Basically one-to-one means that everything in your range has somewhere to go in the, everything in your domain has somewhere to go into your range, right? It goes to a unique place in your range. onto means that everything gets covered. Okay, so this is an example of one-to-one and onto. Everything in your domain has somewhere specific to go into your range, right? And everything in your range gets mapped to. There's no dots that do not have an arrow going to them. Every element here goes to its own dot, right? So this one and this one, for instance, don't go to the same place. Okay, everything is very straightforward for one-to-one and onto. To have onto and not one-to-one means that everything in your range may be mapped to by several different things in your domain. Okay, so this is onto because everything is covered, but it is not one-to-one because this one and this one both share the same destination. Okay, now if these two had their own destination, then it would be one-to-one, right? So the next case is one-to-one and not onto. So here it's one-to-one because everything has its own place to go. However, it is not onto because everything is not covered. There is this lonely guy here that does not have a pair, right? He does not get mapped to by our transformation or by our function. Okay. So to see something that is not one-to-one or onto, here it's not onto because this has no mapping. It is also not one-to-one because both of these guys go to the same end result, the same place. Okay. So one-to-one. Every element in the domain, okay, so let's look at this one. Every element in the domain is mapped to a unique vector in the range. Okay, so for instance, these two go, let's take this one. These two go to the same place. There's not a unique output for each of these inputs. Okay. Onto means that every element in the range is mapped to by a vector in the domain. Okay, so that means everything in your range has a pair originating in the domain, right? Or a partner. Right, so let's bring this to another theorem. A linear transformation from Rm to Rn is one-to-one if and only if the transformation of some, or let's say any vector x to the zero vector has only the trivial solution of x itself being the zero vector. Okay, so the only way to get to the zero vector is to plug in the zero vector, then you will be one-to-one. Okay, so an example. So suppose we have a transformation from R3 to R2 as a linear transformation. We want to prove that T is not one-to-one. Okay, not one-to-one. So before we go any further, remember we had something similar with having only the trivial solution or not having the trivial solution. And that had to do with what we like to call linear independence. Okay, so remember, what is our definition of linear independence? I don't have it here because this is not the linear independence section, but I suggest that you go back and look at our definition of linear independence and compare it to this definition, right? Our definition for linear independence is that if we have a set of vectors, the only way for us to make a linear combination of those vectors and get the zero vector out is if all of those coefficients are zero, right? So here we're saying that if we have a linear transformation where we plug in x to our transformation and get the zero vector out, right? Very similar to a linear combination with 0 on the right hand side, okay? Having only the trivial solution, right? So this is very, very similar, if not identical, to our definition for linear independence. So suppose that we have a transformation from R3 to R2. That is a linear transformation. We want to prove that this transformation is not one-to-one. So we want to prove that basically we have two elements from the domain that can get mapped to the same element in the codomain or in the range. Okay, so we want to show that we have two things that we can plug in that will get me the same thing out. All right. Of course, that's not how we're going to prove this, but that's what we want to prove. So let's do a proof. Okay, so this is our example. So remember, we're a blank slate. So I need to assume that I have nothing. So what do I need? I need this transformation, right? Which means that I need things in R3 to go here. So this is actually more of a roundabout proof because we actually are not going to just be plugging stuff in here. We're going to be using concepts that we understand in order to prove this. Okay, so let's say that we have this transformation, right? We want to show that it's not one-to-one. So let's just think about the sort of matrix that this forms. Okay, what kind of matrix do we get from R3 to R2? So remember, this is going to be my number of rows. This is going to be my number of columns, right? So it's reversed. It's reversed from the dimension norm that we say, right? So this is going to give me a 2 by 3 matrix. Okay, so A is an element of real matrices that are 2 by 3, right? That's how we say this thing here, right? 2 by 3 matrices with real entries. So that means that the number of variables I have, which is 3, is more than the number of equations that I have, which is 2. Right? So if I have more columns than I do rows, more variables than equations, then that means that when I simplify it, right, when I reduce it to reduced row echelon form, I am going to have a free variable. So what happens when I have a free variable? When I have a free variable, that means that I have a linearly dependent system. Okay? If I have a linearly dependent system, that means I have infinite solutions. And if I have infinite solutions, then that means I have infinite ways to create the same vector, right? Or that AX equals the 0 vector, which is meant by this transformation, right? What's the definition of a transformation? Some matrix A times X equaling 0, right? If we come back to this definition of a transformation, right? T of X is A times X. Okay. And X in this case is not going to be the 0 vector because there's an infinite number of ways for this to happen because I'm linearly dependent, right? I have a free variable. Therefore, my transformation from R3 to R2 is not one-to-one. Okay, so this is still a direct proof, but this is what I would call a non-algebraic proof. Here, for this proof, you're using your understanding of the concepts of the course so far to prove what it is that they're asking for. Now, these sort of proofs I feel are more difficult because it means you have to have a very solid understanding of the course up to now. Okay, so if you're having a problem following this, I suggest that you kind of go through this again. So again, in order, what I'm doing here is I'm saying I have this sort of thing going on. I want to come to this proof or to this end result. So there's not math for me to do here, but instead what I need to do is I need to use this theorem, which means that this is true, 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 right? So it's a logical flow of ideas rather than a set of calculations, okay? I feel like this is harder for students to grasp, but again, that's the way that this course is, right? So to review just this one more time without having to rewind, I need to show that this linear transformation is not one-to-one, which means that I need to show that I have more than one thing ending up in the same place. So far, the only way that we've seen that is when I have infinite solutions to a system, right? If I have a system that has infinite solutions, I have infinite ways of going to the same vector, right? The same output. So I basically need to just show that I have infinite solutions. Well, what does it mean to have infinite solutions? Infinite solutions means that you are linearly independent. So how do I show that this is linearly independent? Well, I have some idea now because we've talked about matrices and we've talked about reduced row echelon form. And so if I look at the matrix that's formed by this transformation, right, even though I don't have an actual transformation, let's say I just made one up, it would have 2 rows and 3 columns. And reducing that would give me a free variable. But we also have, right, I'm not showing you that, I'm not doing the actual math, but we do have a theorem that we talked about in chapter 2, where the number of variables being more than the number of equations means that you're going to have a free variable, i.e. you are linearly independent, right? And linearly dependent means that you have infinite solutions, okay? So infinite solutions means that you are not linearly independent, which is why I said go back and look at the definition of linear independence. And so that's basically how we prove this one, by using the concepts that we've developed so far, okay? So let's look at another theorem. So let's say that we have a matrix A that is n by m. So it has m vectors, and each of these m vectors has n elements, right? And that we have a linear transformation from Rm to Rn, right? So number of columns, number of rows, number of columns, is given by a linear transformation T of x, where that transformation is this matrix times any vector x that I have, right? So my vector x should have n elements in it. Then for one-to-oneness, right, all of these are going to be for one-to-one, we can say that T is one-to-one if and only if the columns of A are linearly independent. So now what we get to do is we have a new way of showing one-to-oneness. So let's say that we went back here, okay? And I needed to prove this again. I can now prove this a different way, because since this is a 2 by 3 matrix, I have 3 column vectors that each have 2 elements in it. That means I have 1 extra vector, right? In order to be linearly independent, I need to have only 1 vector or 2 vectors. If I have more than 2 vectors, because there's only 2 elements in each, it is not going to be linearly independent. So I could now reprove this by using that formula instead, which would be actually much shorter than this, okay? So that would be another way of proving that, using concepts rather than calculations, okay? If A is equivalent to B, meaning that if I were to take B and reduce it down using row operations and come up with A, right, or the vice versa, right? So I start with A and I reduce it down to B, and my B is in echelon form, then T is one-to-one if and only if B has a pivot in every column, okay, in every column. So if every column vector has a pivot position or a leading variable in it, then I can say that I am one-to-one. So this is another way now for me to verify something is one-to-one. So that means that I'm going to have no free variables, okay? In order to have a pivot position in every column, I cannot have a free variable present, okay? Which is basically how I prove this. I basically said I have a free variable, which means I am not linearly independent. I have a linearly dependent matrix. So I don't have the trivial solution as the only trivial solution. So I'm not one-to-one, okay? The next thing is that if n is less than m, right? So if the number of rows is less than the number of columns, which is what I had here, the number of rows was less than the number of columns, okay? More columns than rows, then T is not one-to-one. So again, this, along with the free variables, is how I proved something was not one-to-one in the previous example. Okay? So now you have sort of 3 methods of showing something being one-to-one or not. Onto. What are the things that I have for onto? Okay, so really what's going to happen here is I had 3 things. They're going to be mirrored now for this onto portion as it was in the one-to-one. So T is onto if and only if the columns of A span Rn. the range. Okay, so do my columns span the entire range, right? Do they span the range that I'm going to? So now I'm going to ask you a question. Would this linear transformation span the domain, right? Would this be an onto transformation? Okay. Now the answer to this is going to be, drum roll, I'm going to give you a second. What do you think? Yes or no? The answer would be yes. Okay. The answer would be it does span. We'd have to do an additional check, but most likely yes. Okay. It would span because I have 3 column vectors in two variables. Okay, 2 entries each. So as long as I have 2 of them not being the same, as long as there's 2 different ones, so at least one is not a linear or a scalar multiple of the other, it should span R2, because then I'll have 2 of the 3 vectors being linearly independent, and that's all I would need to span that space, right? So that would give me a spanning set. So in the previous example, it should span Rn, okay? Because, and since it spans Rn, it spans the entire range. Rn is my range. So if A is equivalent to B, B is in echelon form, okay? Then A is onto if and only if B has a pivot in every row. So I can still have a free variable, but every row has to have a leading variable. There can be no 0 vectors, okay? No 0 rows, okay? The last one is that if the number of columns is more than the number of rows, okay? Oops, looks like this should be switched around. Sorry, guys. So I switched. Oh no, I did that right. Apologies. This is columns. So n is the number of rows. So if I have more rows than I do columns, then t is not onto. Sorry. Okay. So if I have like 10 rows but only 2 columns, it's not going to work. Right? So that's a couple of ways to check for one-to-oneness and whether or not something is onto. So let's take that now and put it into an example, because I can talk about theorems all day, but if you don't see it actually being used, it's not going to make any sense. So let's consider the linear transformation from R3 to R3 that's given by the following transformation. Okay, so if you notice, I have 1, 2, 3 entries. Okay, so that's R3, and I have 3 variables, right? So then my output, right, when I plug in my 3 elements from whatever vector I multiply this by, right? So my x that I plug in, my domain, has to have up to x3, because if you look here, it goes x1, x2, and x3. There's no x4, no x5s, nothing like that, right? The largest one you see is x3. So my input, my domain, has to be R3, okay? The vectors I get out are going to look like this, okay? So that's an entry here, an entry here, an entry here. So that's 3 entries. That's R3. So I'm going from R3 to R3, right? And I know that because the largest subscript here is x3. And then when I'm looking at what my vector looks like, there's 1, 2, 3 entries, okay? So let's say I take a vector x that is 1, 2, 3. It's just something simple, right? Then plugging in the vector x equals 1, 2, 3 into your transformation will look like this. And then obviously you got to actually plug in all of your values. So everywhere I see x1 is a 1. Everywhere I see x2 is a 2. Everywhere I see x3 is a 3. So I do this math, right? This is going to be 2, 4, 7. This is going to be a 5. And this is going to be another 7 as well, right? 7, 5, 7. So this was my input from my domain, and this is my output from my range. Okay, I'm going to go backwards real quick to talk about what it is that we just did in terms of all of the abstract things that we just covered, right? So more specifically here. Okay. So what I did was something was in my range if and only if A times the matrix that I have gives me W. So in this case, the W was 757, right? The X that I had was the 1, 2, 3. And the A matrix, I haven't written out specifically, but we will see that in a second, right? So what I basically did was some matrix addition, but we have not seen matrix multiplication, but we haven't seen multiplication yet, so we're looking at it in terms of plugging things into where they have to go function-wise, right? So we'll see in the next section matrix multiplication and exactly what that is, okay? So T of X equals A times X would look like this. 2, 1, 1, 2, 1, 1, 1, 2, 1, 2, 0, because there's no X third term, 1, 3, and 0. So that's the A matrix for my transformation. And if I take this and I multiply it times my vector, so we haven't talked about multiplying matrices and vectors yet, or a matrix times a matrix, but what happens is as I take this entire row and I multiply it term by term times this column, and I add the terms together. So 2 times 1 plus 1 times 2 plus 1 times 3, which is exactly what I had here. Okay. Same thing here. 1 times 1 plus 2 times 2 plus 0 times 3, which is exactly what I had here, right? 1 times 1 plus 3 times 2 plus 0 times 3. So term by term, first term times first term, second term times second term, last term times last term, and I'm adding those products together, right? And it's exactly like if I were to just take my elements and plug them in to my transformation in its transformation form. Another way of thinking about that is taking 1 times the entire first column, right? Turning it into a linear combination. 2 times the second, and 3 times the third, because we've talked about this before, right? Oops. And that will also give me my 757, right? So the way I just showed you, outlined to you, is what we're going to see in the next section. However, we have talked about writing these things as linear combinations in this form. So if I were to take this and reduce it down to row echelon form, then notice that I would have a pivot in every row, and also every column. So what does that mean? Well, if there is a pivot in every row that I'm onto, if there's a pivot in every column, then I am 1 to 1. So that means that this transformation is 1 to 1 and onto. Okay. All rows and all columns have a pivot position. Therefore, A is 1 to 1 and onto. So let's say that this was all zeros here. Okay. If this was all zeros, then not every column would have a pivot, and also not every row would have a pivot. And so I would also be a dependent system. So I would not be onto, I would not be 1 to 1. I would be neither of those things. Okay. So just a quick check for checking for 1 to 1 and onto-ness, and also how to plug in something to a transformation. Okay. So now we want to talk about the geometry of linear transformations. So what we're doing is we are transforming something into something else, okay, which is a lot of what linear algebra is about, actually. Okay, is taking a space and manipulating it into something else. Pretty much everything that we do is some form of a transformation, although we will not always talk about it in the lens of a transformation. Pretty much everything we're going to do is some sort of a transformation, though. A large part of it, I should say, not everything. So what we're going to do is we're going to talk about what transformations look like in general and how they transform the space that we're in. So they transform our vectors, but they also change the geometry of the entire space that we are working in. Okay, so let's go through these one at a time. I'm going to go through this rather quickly because there's a lot to go through. So you can take your time and go through this video again, or look at the write-up that goes with this, because all that information will be there as well. So let's first talk about reflections about the x-axis. So if my transformation looks like so let's look at this a little bit. So xy for us would be a vector that has two entries. Okay, so here they're looking at it a little bit differently than we do standardly, because I pulled this from a different textbook. So basically, if we were to plug in, instead of a vector that has three entries, x and y is our two entry vector. Okay, they're just not writing it in a vector notation, which is fine. It's easy to adjust to. So let's say we plug in a vector that has two entries, okay, and our transformation is given by that second entry being 0. Okay, so notice that we are plugging in two things, x and y. My transformation matrix will look like 1, 0, right? Because the first equation, right, has only an x and no y. The second one has no x and a negative y, right? So this would be the transformation matrix, okay? And so my transformation here would take something at the xy, and it will flip it around because it's making the y be negative, right? So I'm going from over x and up y to now being over x and down y. That is the transformation compared to what I plugged in. Okay. So one way to tell what a transformation does is by plugging in what we call an elementary vector. Okay. An elementary vector, or what we also like to call unit vectors, okay, are the vectors that make up the axes. So 1, 0 means you go over 1 and up or down none, right? So this is representative of the x-axis, and this is representative of the y-axis, okay? So if I plug in the vector representation of the x-axis into my transformation, nothing happens because the y portion is 0, so nothing changes. So that becomes my first column vector, okay? If I plug in 0, 1, my representation of the y-axis into my transformation, nothing happens for the first element, but the second element turns into a negative, and so that becomes my second column vector, okay? So that's how I form my linear transformation. All right, so for reflections about the y-axis, that means that the x's need to be negative. So it works the same way, okay? So instead of the y's being negative, it's the x's that are negative, okay? So again, if I were to plug in my elementary vectors, my E, we'll call E1, E2 because I'm in R2 here, right? Two-dimensional system. I only have two axes, the x-axis and the y-axis. This is how they get changed. So basically what that means is if I take any vector and multiply it times this matrix, it will reflect that vector across the x-axis. If I use this as my transformation matrix, it'll reflect it across the y-axis, okay? If I want to reflect it about both, then I have the transformation yx, which is this matrix, right? So that will flip it around, reflect it around this line. If you remember your regular functions, all inverse functions are reflected across the line y equals x. So this might help you in your calculus classes. If you need to find some inverse functions, you can use this transformation. Okay. So in 3 dimensions, if I want to do a reflection about the xy plane, right? So that is the plane that's made by the x-axis and the y-axis, right? So now I have a vector that is moving outside of that plane. If I want to reflect it across that plane, I'm reflecting it across z, right? If it was positive in z, it now needs to just be negative in z, but its x and y coordinates have to remain the same. So the x and y coordinates remain the same, but it gets flipped across the z-axis, right? X-axis, y-axis vector, z-axis vector, and it flips across that, okay? If I want to flip across the xz plane, that means that x and z needs to remain the same and y needs to change. So if you come here, if we're going from here straight here, z stays the same, x stays the same, y is the one that is changing, okay? Again, the xz plane is the up and down plane with the left and right plane, but I need to go across the y-axis. So that is the one that is going to change sign. And for the third one, it's the same thing. If I want to reflect across the yz plane, it's the x's that are changing. So that is what needs to become negative. So now let's talk about orthogonal projection. This is stereographical projection. We actually talk about this a lot in this class, much later. But if I want to basically project a vector down, so you can think about it as if I need to create the shadow of a vector, right? So I'm projecting the vector onto an axis. So if I had a light on top, this would be the shadow that's created straight down, right? So basically what I'm doing is I'm completely taking away the up and down portion of this vector. So there is no y component in that transformation matrix, okay? So again, if you ever want to see what your transformation matrix is supposed to look like, you just take your axis vectors and you plug them in to your transformation, okay? That's the easiest way to see what your transformation matrix should look like, or is going to be. If I want to project it across the y-axis, then that means that I no longer have a left and right, so the x becomes 0, and all I have is the y component, okay? This is typically more, well, it's very useful in this class, but it's used a lot in physics in 3 dimensions and in your calculus 3 courses as well, where again we call it stereographical projection. So let's look at it in 3 dimensions, okay? So if I want to project it onto the xy plane, that's the plane that's down here, if I have a vector that is going upwards, it has an up and down component, I'm going to take away the up and down component and bring it back into our regular x, y 2 dimensions that I'm used to. Okay, so imagine now I have a vector that's coming out of the screen and I need to project that into the 2-dimensional world. That's what this is doing. Okay, so it's coming out into the 3rd dimension, but I'm playing around in 2 dimensions. So I need to put a light above it and look at the shadow of it in the 2 dimensions. That's basically what's going on. So again, I'm taking away the 3rd dimension and I'm keeping it in an x and y coordinate system, okay? So if I need to project onto any other plane, xz for example, I'm taking away the y component. So the y component is 0, but I have my x and z world still available, okay? If I need to project onto my yz plane, which one do you think I'm going to take away? I'll give you a second. What do you think that this transformation matrix will look like? Okay, I mean, there's kind of only one case left, right? Obviously, this column will be all zeros, and I'll have ones for the x and the y and the z positions. All right, so now let's look at a separate operator of rotations. Okay, so let's say we want to do a counterclockwise. So if you think about trig, all angles go in a counterclockwise manner. We can do the exact same thing that we would normally do, but it's provided for you, right? So when I say exact same thing, I mean taking the unit vectors, the standard vectors, and plugging them into our transformation to get what we get out. But for rotations, it's a little bit different. We can do the same thing, although that depends on your rotation. So the standard matrix for a counterclockwise rotation in 2D is cosine sine and then negative sine cosine. So you have cosines on the main diagonal, sines across the other way, the other diagonal, with the upper right-hand corner sign being negative. Okay. Now, if we do rotations in 3 dimensions across different axes, it's a little bit different. So notice that if we are keeping the x-axis fixed, and that's the rotation that we're going across in a counterclockwise direction, we're keeping that x unit vector as a 1, 0, 0, that standard vector. So the axis that we're rotating about has that standard vector, that standard unit vector, 1, 0, 0, and then we have our standard rotation matrix in place for the other vectors that we're using. Okay, so now let's say that we want to rotate across the y-axis. Then what's going to happen is we're still going to have the standard rotation matrix, but this portion of the vector is going to be in place across where the x-axis, this x-axis vector is, and we're going to have a 0, 1, 0 here because we're maintaining that y-axis as staying in place. And then this last vector would do the same thing. Okay, right? So for the y's, everything that has to do with y is 0. Okay, 0 across, and it's 0 here. And then the entries of the standard matrix for the rotation go in the respective places, right? Cosine in the upper left corner is in the upper left corner. Sine is going to be rotated, however. It's going to change signs. And this cosine here is going to stay on this main diagonal as well. Okay. And then if we move for the z, the same thing. This is 1s, 0s everywhere else, everywhere the z's are located at. And then we have our standard matrix for counterclockwise rotation along z. Okay. All right. Now let's say we want to do contractions or dilation, so basically stretching or pulling things in. Right. So if I'm in 2 dimensions, I'm really just going to shrink this vector appropriately. So the transformation I have is kx, ky. And so I'm just kind of moving everything in to be smaller. So if I had the unit square, right, the unit square would shrink down if k is less than 1, or it'll grow if it's larger than 1. So we just have a growth or a shrink on the x and y axis. Okay, so that's what the standard matrix for a contraction or dilation looks like as a transformation matrix. In 3 dimensions, it's the same thing. You're just adding that extra standard vector, okay, for the z direction. If we want to do a compression in a single direction, then we just have k for that single direction, and the other one stays as the unit vector. Okay, so k1 is going to shrink or expand in the x direction here, right? So it's going to compress or expand in x. If I want to compress or expand in y, then this will be a 1, 0, and this will be a 0, k, and that will change my my y's, my up or downs, to go either up or down by a factor of k. Okay, so here I'm compressing by k, here I'm expanding by k in the upward direction by k. Okay. So now we have what's called a shear, which is you're just kind of tilting everything in a certain direction. And so if we want to kind of tilt it top-wise, left or right, like a leaning building, then we're putting the k in the top portion, not on the main diagonal. Okay. If we put it on the bottom portion, then we're shearing the bottom half, like you're pulling and you're tugging on one of the edges. Okay. So here what we have is the image of a transformation of the unit square. So unit square has lengths of 1. And what that transformation looks like under different sort of changes. Okay, so as you can see, we have a shear and a growth, an expansion. Right here we just have an expansion in 2 different directions. So here the x direction has been expanded by a factor of 3, and the y direction has been expanded by a factor of 2. So if you understand that, right, because this should be just the standard 1, 0, 0, 1 sort of base sort of set of vectors, okay, that's what we call a unit square. If this is our transformation, it's going to take this and it's going to grow it respectively in its appropriate directions, right? As we just saw, you know, through this huge list of things that we did, okay? This was reflections, okay? So if we continue down here, right? Here, the x direction is going to stay as 1, which it does, right? The base stays as a factor of 1. The length grows by a factor of 2, okay? And we are also growing a shear in this direction. So if I actually took the length of this, it's going to be more than 2, right? But that's what happened. I kept this as 1, then I grew this as 2, and then the shear sheared it over 2 units. So what would have been here at a height of 2 has now moved over 1, 2 units, okay? And what would have been here at a height of 2 has moved over 1, 2 units to be the edge, right? So basically what we're doing is we're taking this unit vector, 0, 1, and we're saying, what does this do to it? Nothing. Then we take this vector, 0, 1, and we say, what does it do to it? It turns it into 2, 2. So if I go 2, 2, the vector that was here is now transformed into this vector, okay? So that's the 2 ways of thinking about this, right? Looking at each of your base vectors, 0, 1, or I guess this would be 1, 0, and 1, 0, and what happens to it here? It stays the same. Then looking at this basis vector, right, this standard vector, 0, 1, and what happens to it? Well, it turns into 2, 2. So this vector now is going to be 2, 2. This was the left side. That's what happens to the left side. And now those 2 things form the basis for my parallelogram, right? So it changes this into that manner. Same thing here, okay? I had 0, 1. Under this transformation, it changes it to 2, negative 1, right? So 0, 1 now becomes 2, negative 1. So this line here corresponds to this bottom vector, okay, this new vector. And this 0, 1 turns into 1, negative 2. So that means I go to 1, negative 2. That's the other edge, okay? So this becomes one edge, and that becomes the other edge, and then I finish out my parallelogram. And that's how I transform this vector. So this space that I had gets transformed into this crazy kite or parallelogram that we have here, okay? Now if we look at it just in terms of, oh, well, where is it saying I'm doing here? Well, it's telling me that I have a shear in the bottom direction. I have a shear in the top direction. I'm also growing by 2 in the x direction, and I'm going a negative 2 in the y, so that's flipping across the x-axis, right? So we can look at the components here and say, oh, it's doing each of these things, but it is way easier to think of, well, this was one base and this was the other base, so what does that transform to under this transformation? And then just finish out your parallelogram to see how your space has been changed now, okay? Right. So I know it's confusing, but again, we will 100% be revisiting transformations later on. We will be talking about them quite often. This is just to get a basis of the understanding of what these linear transformations actually look like. We're just laying down some foundation. Understanding is very similar to a function. There's a domain, there's a range, one-to-one, onto, and using the idea of linear combinations and things like that and dependencies to flesh out the ideas, right? So here, this is another transformation of my basic unit vector, okay? So here's reflection across the axes. So this is just -1, right? So what was 1, 0 is still 1, 0. And what was 0, 1 is now 0, -1, or down here, which reflects it across this axis. Okay. Here, same thing. What was 0, 1 becomes -1, 0, so it goes to -1, 0. This one stays the same. And then I just finish creating my square from my new vectors. Okay. However, sine, cosine, and sine is a little bit different. Right? So my x changes by cosine of some angle, right? And then the up and down portion that goes with that changes as well, right? So remember, cosine is the x, sine is the y. So what was 0, 1 is now cosine of your angle, sine of your angle, right? So that's where it terminates at, and that's the vector that you get. What was 1, 0 now turns into a negative sign. So negative sign means that you go down, right? And then you have your cosine, which tells you how much you're going to go over. But obviously these values are going to be opposite. So this negative sign means you're actually going up, and this cosine of what would be negative is going to bring you this way, right? So that brings you to this vector, okay? And then here you have a shear transformation. So again, your 1, 0 stays the same. However, your what was 0, 1 now turns into going over A in the x direction and up 1, and that's where that vector terminates. So you go from here to now being here, and that's your corner of your parallelogram. So then you just draw your other sides of the parallelogram to get your transformation of the unit square. Okay, so now what we have here is a little bit different sort of image to interpret. You can kind of interpret it two ways. You can think about this UV as a single vector, right, and shift it to be down here. So if you think about it, this one vector is what it has a length of in the x direction of 1, 2, 3, and it goes 1, 2 up. So this would be 3, 2. So if you throw it into this transformation, it will change quite a bit, right? So remember, vectors kind of don't have a starting point. I think an easier way to look at this transformation is to look at the vector u. Okay, so even though you don't see a vector here, this vector u is 1, 1. And if you throw it under here, then u will be transformed from 1, 1 to 1, 2, right? So if you think about this as the square that u is at, its square will now move a little bit, right? So 0, 1 will now get moved to be 0, 2. Okay, so this, 1, 0 here. So this will move to 1, 1, right? And then 1, 2. So as you can see here, this has been sheared to 2 and 3 to this, and then this V, if you think about the square, the corner of the square that makes this one, it'll be the same thing, right? So if this 1, 1 gets moved to 1, 1 as the first part, and then 1, 2, so what was right here gets moved to 1, 2, so 1, 2, you have a sub parallelogram here, okay? And then when you finish that parallelogram, the end of that parallelogram is going to be here. Alright, so it might be confusing, but if you drew this square with the upper right corner at the dot u, and then you put the unit vectors into that transformation, right, this bottom corner, 1, 0, will now be at 1, 1 at this diagonal. Okay, and the up and down corner will now be moved to 1, 2, or over 1, up 2. So you would have a small sub corner of your parallelogram, and so when you finish the parallelogram, this will be where that corner is, right? So that's how you mark the endpoint of u to the endpoint of the transformation. And you would do the same thing with the v, right? If you took this sort of square that it's on, right, so you would have 1, 2, 3, 4, and you put it under this transformation, it'll go to 1, 1, right? So it'll go to 4 and 4. That would be the lower part of it, would be this vector. And then if you took the upper part and you put it in this transformation, it would go somewhere up here, right? It'll go 4 and then to 8. And so then when you draw your parallelogram, this will be the end of it, right? So you'd have to do some extra animations here, some extra drawings to see how you go from here to here. But you can do it by looking at the unit square and how the transformation changes your unit square, right? So basically what I said was, if this is the vector, if this is the point, that point gets shifted to that point. Okay? So if this is the upper right most of a unit square, under this transformation, that's going to get moved to here. Okay? If this is the upper point of a transformation of a unit square, of some square, that's going to get moved to here. And vice versa for this transformation. Okay? So practice around, play around with that a little bit, but I think that's the easiest way to understand this U to V portion as a transformation of point U to transformation of point V. Alright. Hope that helps you guys. I know it's a little bit longer of a video, but it's because we had to go through all of these images. Okay. Good luck. See you next time.